Now, whenever we're going from a regularly written number to expanded form, always start at the farthest right number. I know it's a little counterintuitive because we're used to going left to right, but the idea is based on how large the number is, there might be so many decimal places to the left or numbers to the left, but they're always, the farthest right is always the ones place. That's what's fixed. So this is the ones. As you go over, it increases by a power of 10. So this is the tens. This is the hundreds. And the way we will express that is, remember that anything to the 0 power is 1. So 1 is really 10 to the 0. 10 being raised to the 0. 10 to the first. So the idea is we can write expanded form. Since our number system is based on base 10, we can say, okay, we have 2 ones, which I'm going to write as 10 to the 0 because I want to see this incrementing on powers of 10, plus 3 tens. Notice as we move to the left, you'll see the exponent on the 10 increases by 1. So next over, it starts at 10 to the 0, and we'll have 8 10 squareds. And that would be our answer in expanded form. Now, if you haven't had a chance to, if y'all would write this in expanded form, take a minute or so to do so based on what we just discussed. So with this, if I'm trying to write it in expanded form, do I want to look at the farthest to the right, which in this case would be 6, or the farthest to the left? Where do I start? We always start with the ones place, right? So even though we read left to right, the issue is if we start here, I don't know just by looking at it what number this is. Like, I don't know what this is representing unless I look more carefully. Oh, it's in the 10,000, but I know this is in the ones. Does that make sense? Because the farthest to the right is always the ones. And then as you move over, you can increment up. Now, if I looked at it, I could say, oh, this is in the 10,000s. But do we see that's not an immediate thing? I'd actually have to look and say, how many places are there? Whereas when you look at the farthest to the right, it is immediate that this is a 6 in the ones place. So remember, if you're going to expanded form, always go to the farthest right. That's the ones place. And then as you move over to the left, you go up by a power of 10. So 1 times 10 is tens place. 10 times 10 is 100. So next over is the hundreds. 10 times 100 is 1,000. And then 10 times 1,000 is the 10,000s. So in our mind, we remember, okay, what's fixed? The ones place. Where's the ones? Farthest to the right. And now as we write this out in expanded form, always start with the ones. The ones should always be paired with 10 to the 0. And then the pattern is, as you move to the left, you increment the exponent on the 10 by 1. So we're going to add 7 times 10 now to the first power. 10 to the first is 10, so that's why it's in the tens place. As you move over, you increment the exponent. And we're kind of writing in a funny way, we're writing right to left, but that's because we're increasing up ones, tens, hundreds, thousands, 10,000s. Now, are there any questions that we could maybe clarify or answer related to this topic? Okay, if we're good, then let's do the reverse. Do y'all see that this is now written in expanded form? And you want to make sure you can understand, okay, if it's written in this expanded form, what number is this representing? How do we normally express it? So my hint to everybody would be to simplify each term, figure out what this is, figure out what this is, what this is, what this is, and what this is all separately, and then add them together. And as y'all work on it, my reminder to everybody is to remember 10 to the 0 is 1, 10 to the first is 10. And if you type this into your calculator, you can find all the rest of them. Remember, it's 10 exponent button 2. So let's take a minute to work on this ourselves. So I've simplified what each exponent on the 10 means. 10 to the 0 is 1, 10 to the first is 10, 10 squared is 100, 10 cubed is 1,000, 10 to the fourth is 10,000. Then we multiply. 4 times 10,000 is 40,000. 5 times 1,000 is 5,000. 0 times 100. 0 multiplied by anything is just 0. Plus 1 times 10 is 10. Plus 7 times 1 is 7. Adding all these together, we get 45,017 as our answer. Any questions that we could answer here? Do y'all see that these type of questions are like either direction? Kind of going from our number to expanded form or expanded forms to our numbers. And that's how a lot of chapter 4 is. It's kind of going this way to this way or this way to this way. So now let's focus on the Egyptian symbols. I'm going to zoom in a little bit. As a reminder for the Egyptian symbols, they are just kind of what you see is what you should write. So for instance, if we want to represent 50, we're going to have to write 5 10 symbols. And usually you could group it in whatever order you want. Like the fact that these are stacked is just to save space. In the Egyptian symbols, stacking things doesn't mean anything. It's just, I didn't want to write 6 of these out linearly because that would take up a lot of space. So what you'll do is you'll carefully find which symbol is this. And since there's one of it, we have one of that number. Continue that. Which symbol is this? Since there's 5 of it, we have 5 of that number. So I'd encourage you to translate each group piece at a time and then add everything together. So translating piece at a time, we see this symbol that I highlighted in green stands for 1 million. And we've got one of those, so we have 1 million. Okay, in blue, the symbol stands for 10,000. We count it, we have 5 of those, so that would be 5 10,000s or 50,000. Next up, we've got the spiral, each of which is 100. We have 6 of those, so that would be 600. Next up is this heel bone. Each stands for 10. We have 5 of them, so that's 50. Finally, we have the symbol for 1, and we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Adding all these carefully together in our calculator, we would get 1,050,000 658. Do you all agree with that notation? Any questions here? If not, then let's do the reverse. Let's go from our number system, 3,425 is an Egyptian number. Anytime you're doing this, it helps to say the word verbally, like I just did, 3,000. That tells us there's 3 1,000s, 400, 4 100s, 20, 2 10s, 5 1s. So if y'all would write that out, remember we use the largest groupings to the left down to the smallest to the right. Now, if we would find it helpful, of course, you could just write it down instantly, but perhaps writing it in expanded notation helps us know exactly what our groupings are. So I'm going to say there's 3 1,000s. Well, I guess I should start from right to left like we normally do with expanded. So 5 1s plus 2 10s plus 4 100s plus 3 1,000s. Here I'm choosing not to write exponent notation because the Egyptian symbols are incremented based on power, like just 10, 100, 1,000, not 10 squared, 10 cubed. So that tells me I need 5 1s. So each one is one of these lines. So 1, 2, 3, 4, 5. 2 10s. So 2 symbols for 10. 4 100s. And then 3 1,000s. Do you agree with something like that? Now, what if this was multiple choice and the answer choice looked like this? Instead of having these 2 under, it had it next to it. Would that change it? No, because the location for Egyptian doesn't matter, right? It's just a preference. Okay, good work, everyone. Now let's do Roman numerals. Now, the one thing to remember before y'all get started here with Roman numerals is the order for Roman numerals matters. The normal order is that it's largest values to the left down to smallest values to the right. And anytime you're out of that order, it's intentional because they want you to subtract the 2 things. So if a smaller symbol ever comes to the left of a bigger symbol, you're supposed to take that smaller number away from the bigger number. So for instance, before y'all get started here, let's just do something as a review off to the side. If I was looking at DC or CD, do y'all agree I'm using the same 2 symbols, but I'm switching the order? So looking at the way it's listed, 500 is D, 100 is C. So do y'all agree here I'm going in descending order, largest to smallest? When it's in descending order, bigger to smaller, then you just add everything together. So that'd be 500 plus 100 is 600. However, In the other case, now we've got the 100 coming written before the 500, that's out of order. So for the Roman numerals, if you ever have this out of order, it's implied that you take the smaller away from the larger, and that would represent 400. So with that in mind, why don't we attempt this next one? Now with time, we might just be able to read it and know, and that's great. But if we wanted to kind of show our work step by step just to make sure everything's going correct, then what we could do is we could just translate each letter and check, is everything in order? If so, add it all together. If anything's out of order, we know we take the smaller away from the bigger. So listing this out, I'm going to write below what they stand for. D represents 500. C represents 100. 100, we're in order so far. Okay, now X represents 10. L represents 50. So I might highlight this to remind myself, this is out of order. So we actually need to take the 10 away from the 50, right? Continuing that idea, the V is 5, 1, 1, 1. Everything else is in order. So in my mind, I'm just going to say this is 50 minus 10, which is 40. So I'm going to add these together. 500 plus 100 is 700. 40 plus 5 plus 1, 1 is, I believe, 48. So do y'all agree with 748 as our answer there? Good. Let's similarly translate this next phrase, and then when you're finished, write 296 as a Roman numeral as well. So everything's in descending order until the last two. They're written out of order, so mentally I know take the 1 away from the 5, and that represents 4. So we've got 500, 600, 700, 750, 760, 770, 780, 784. Do y'all agree with that? Now the next one up, 200. I know I can break this into little pieces. So this is 200 plus 90 plus 6. Now 200 is just two 100s. So that would be CC. Now, in terms of 90, do y'all agree I could write 9 tens, but we want to try to write it as efficiently as possible to be correct in the Roman system. I could write a 50 and then 4 tens, but even that's like 5 characters, right? So the fastest way, wouldn't it be to say take 10 away from 100 and only 2 characters? Now to show that, I need to make sure the 10 comes first. So 10 away from 100. And then 6. So CC, oh, I think, did I write it right? Yeah, CCXCVI. So any questions about the Roman numeral system? Just remember, highest to lowest, if it's ever out of order, that means you're supposed to subtract the smaller from the bigger. Okay, now let's go to the Chinese numeral system. I'll have to zoom out a bit here. And as a review, remember the Chinese numeral system is written vertically from top to bottom. And additionally, it's written in multiplicative pairs. So the first thing I would do if I was doing this problem is I would immediately start at the top and pair up the symbols. Each 2 symbols pair together until potentially the last symbol, which just represents the ones place. And then the way we work through this is you translate the top number is always the how many times, and the bottom number in the pair is the power of 10 that you multiply by. So looking here, this symbol is for 7, and this symbol is for 1,000. So the way this would make sense is as a symbol, since it's 7 and 1,000 below it, it's 7 times 1,000 or 7,000. Translate each of those pairs and then add it together. So I'll give everybody a moment to attempt these 2 problems. So next we have 3 times 100. So this next pair represents the number 300. And then we have the symbol 5 times 10, which represents the idea of 50. And then finally, we just have 8 as a straggler. That's implied to be times 1. So adding these all together, we should get 7,358. Now give everybody a moment to attempt the next one if they haven't already done so. Eventually I'll get 684. Now, next up is just the reverse of this idea. Take something in our number system, break it into what powers of 10 it uses, and then write this multiplier times this power of 10 stacked from highest to lowest. So if everybody would take a moment to write 8,639 as a Chinese numeral. So we know this is 8,639. Break it into the pieces. That's 8 times 1,000, 6 times 100, 3 times 10, and then just 9 by itself. So you always write the multiplier times the power of 10. So we find 8 and 1,000. So this is 8,000. Next up is 600. So we have the numeral for 6, the numeral for 100. Okay, 30, 3, 10. And then finally, 9 is just by itself, it's the ones. And that'll be your answer. So if you'd find it helpful, remember you can first kind of break it into the different pieces like I did here and say, okay, that would be 8 times 1,000. And then you just translate piece at a time, multiplier times power of 10, multiplier times power of 10. So any questions here? So next up is Greek symbols. Now, Greek symbols are very similar to Egyptian in that they're just what you see is what it is, written from largest to smallest. So you just have to carefully translate what each symbol means and add them all together. So I'll zoom in here so we can see the table. If y'all would work on these 3 problems. So finding these pieces at a time, we see we have the number for 700 plus the number for 80 plus the number for 6. So we get 786 for the first one. Next, we've got the value for 200, then 30, and then 1. So we should get 231. And then finally, for the last one going in the reverse direction, we want to take what we know to be 300 plus 20 plus 9, and we'll just find each of those. And we should get 329. Good on the Greek symbols. Now, our last set of historical numbers will be the Mayan and the Babylonian. And then we'll do conversions between different bases. Now, an important thing to remember about the Mayan symbols is they're written where the position has an implied power. So in the Mayan symbols, it's not just the symbols that you see on the screen, but based on where they are, you're going to multiply that by a certain number. So if you look at our class formula sheet, you'll see the Mayan symbols, and next to it, it has a reminder that it's written vertically and it increases as you go up. And as you go up, you've got different bases. Now, although there's more bases than these 3, for our class, you'll never need more than the first 3 bases. So what that means is the first grouping of numbers is in base 1. So whatever this number is, when translated, should be multiplied by 1. The second grouping of numbers is in the base 20 location. So whatever number this represents in Mayan symbols should be multiplied by 20. And then finally, the third vertical grouping of numbers is in the base 360 location. So whatever this is in Mayan numerals, we should multiply it by 360. Okay. So I'm just going to kind of write out, I've got these 3 groupings, group 1, group 2, group 3. And then we need to translate. So in the Mayan numerals, a line is 5, a dot is 1. So this is 5, 6, 7, 8, jolly 9. But what base location is it in? Since it's the first base 1, so you do 9 times 1. Now the next grouping is 5, 10, 11, 12. But do y'all see it's in the second grouping? So we take 12 and we multiply that by 20. Okay. Next up, we have the number 5, 6, 7, 8. But since it's in the third location, it's implied that that gets multiplied by 360. Multiply these and then add up the result. Do you agree with that value? So any questions about how the Mayan system would work? As you're trying to decide which grouping it's in, do y'all see how we went from dots to lines? Anytime you switch, that tells you you're in a new group. So like if we wanted the lines to be in this group, it would have been down here. Does that make sense? So we had the dots and the lines, and then the dots and lines started over. That tells you you're in a new group, started over. And we also see the vertical space in between. So then our next is Babylonian, which is similar in that they both have this base representation based on where the letters are written. You should multiply it by a different factor, except the Babylonian numerals remind us that they should be read from right to left, and the values increase as you move to the left. The first grouping should be multiplied by 1. The second grouping, whatever it represents, should be multiplied by 60. The third grouping, whatever it represents, should be multiplied by 3,600. So if everybody would take a moment to figure out how many groups we have represented here, translate what the symbols mean, and then multiply it by the implied base based on its location. So I agree with that as our final answer. Thank you. Yes, I counted wrong. So here, oops. This is 5 ones, right? So I definitely had the error. This should have been 5 times 1, which would make this 5. And now with this correction, do y'all agree with this answer? Okay, thank you, everyone. So yeah, watch out for those small details. So we've done the Egyptian, the Chinese, the Mayan, the Greek, the Roman system. From those, are there any that y'all like to see more problems of to practice, or y'all comfortable to move to questions going between different base numbers? Okay, we're good. Okay. So the last topic from chapter 4 that we learned about was we just did all these historical numbers, but there's many different ways to represent numbers. We've just chosen for our number system to represent them as base 10, which is like we're doing groups of 10. That's why we talk about there's like 6 ones, 5 tens, etc. But we could choose to increment based off of any base. Some common different bases, if y'all have heard of the binary system, that's working off of base 2. So we have 2 directions as we're thinking about these problems. And based on which direction we're going, we're going to have to do a different approach. So if we go from other bases back to base 10, that's what this problem is doing. And in this approach, you just kind of write out what's being described. Similar to expanded form from before, except now instead of working with base 10, we're working with base 7. So the base that you're working with will always be written out in words as the lower right subscript. So the procedure here is you go to the farthest right, always the farthest right because that's fixed, And we're going to say that should be 1 times, okay, our base was listed as 7, but since it's in the ones location, it needs to be 7 to the 0. Plus, and now as we move to the right, we just increment the exponent on the base by 1 each time as we move to the left, I mean. So that's 6 times base 7 now to the first power. Plus, move over, increment the exponent, 5 times base 7 squared. Now, do we see where all these values are coming from in the ordering? So when you go from an other base to base 10, you just basically write out the expanded form, simplify each term, and then that will be our answer. So 7 to the 0 is 1, so this is 1 times 1. 6 times 7 to the first is 7. 7 squared is 49. And y'all agree with this value? Now, when you're in base 10, it's implied, so we don't have to write the superscript sub 10 because that's our implied base. We don't really mention it. So remember, this is the procedure to go from other bases back to base 10. So similarly, if y'all would calculate this, remember you always start the farthest to the right. So just to get us started, that's going to be 0 times 2 to the 0. And as you move to the left, you increase the exponent by 1 each time and write the multiplier. So 0 times anything is just 0. We translate, okay, 2 to the first, 2 times itself 1 time is 2. 2 squared, 2 times itself twice, 2 times 2 is 4. 2 times 2 times 2, 2 cubed is 8. 2 times 2 times 2 times 2, 2 to the 4th is 16, 2 to the 5th is 32, and we can also type this into our calculator. 2 to the 7th is 128. So whenever you have 0 times something, it goes away, but all the others remain. So adding these all together, and did y'all get 182 as our answer? So in both of these examples, we went from some other base, which was indicated because it had the base that we were interested in written as a subscript in words, to base 10 just by writing out the expanded form and simplifying. Now in our next examples, we're going to go the other direction. We're going to go from base 10 to other bases. And to do that, we need a different strategy. So let's look at that. So now we know that we're in base 10 because you'll see that we have a number listed without any implied base to the right. So this is implied to be in base 10 because we're just listing it as a normal number. And they said they want us to go to base 8. So in this example, we're going from a base 10 number to another base. Now we'll all need our calculator out for this. Let's do this one together, and then I'll show the second example for y'all to attempt on your own. So we learned 2 procedures whenever we went through this in class, but I think most people preferred this second method, so we'll go with that. The idea is you always put the number that you start with inside this little box, and then you put the base that you want to change it to on the outside. Always the base 10 number that you start inside the box, the base that you want to change it to outside. And then you get the calculator. And what we'll do here is we'll say 430 divided by 8, and you'll see I got 53.75. Now the thing is, I don't care about the decimal, I just care about that it goes in as an integer 53 times, so I write that, 53. But then since it doesn't go in perfectly, because of this decimal, I know it doesn't go in 53 times perfectly, so we have to figure how close do we get, and then how much do we have to make up for. So to figure out how close you got, you take 8 times 53, which y'all agree is 424. Now we wanted to get to 430. So how far away are we?
6.
Good job, 6. So the remainder is 6. And then you just keep repeating the process. We say, okay, let's divide this by 8. So we take 53, divide it by 8 in our calculator. Goes in 6 times perfectly. But let's figure out how far away we are. That will be our remainder. So we take 8 times 6. That gets us to 48. We wanted to go to 53. So do y'all agree that would be a remainder of 5? And we just keep repeating the process. So now we divide the 6 by 8. 6 divided by 8. And y'all notice in my calculator, now it says the integer part, it goes in 0 times. And that makes sense because 8 is larger than 6. So you write down 0. But 8 times 0 gets you to 0. We wanted to get to 6. So what's the remainder here? 6. And then once you get 0 as the last thing, that's how you know that you stopped the problem. Now the final trick here that you have to remember is the way you write this is you go down and up. So you kind of imagine picking it up and turning it over. So this would be 6, 5, 6, base 8. So this 6 was from here. This 5 was from here. This 6 was from there. So 656 base 8 is a different way to write 430 in base 10. Now, if y'all would take a moment to read this problem and think about, okay, within these changing bases, are we going from a base 10 to a different base, which we just did the practice where you do the division, or are we going from another base to base 10, in which case you just write it out and simplify? Give everybody a minute to attempt this one on their own. So in this example, since it's just 27, there's no superscript. We know it's implied base 10 going to base 2. So this is the case of going base 10 to other base, in which case we set up our handy division. So you put the number that you start with in the box, the base that you want to go to outside, and we just start dividing. So 27 can be divided by 2 13 times perfectly, but then the remainder would be 2 times 13, get you to 26. We want it to be at 27, so that's a remainder of 1. And we just continue to iterate this. Divide this by 2. 6 times perfectly. 2 times 6 is 12, so we need a remainder of 1. Now 2 goes into 6 3 times perfectly. So there is no remainder needed because 2 times 6 or 2 times 3 is 6. That's where we were going to. Continue. 2 goes into 3 1 time perfectly. So 2 times 1 is 2. We want it to be at 3, so that's a remainder. 2 goes into 1 0 times because 2 is larger than 1. 0 times. 2 times 0 is 0. We wanted to get to 1, so the remainder is 1. Now here's where I have to remember the key idea. I kind of start and then remember, imagine flipping it over. So this would be 1, 1, 0, 1, 1, base 2, where this one is there, this last one is here. Since it's symmetric, I'm just trying to point out the ordering. Does that match what y'all found? Any questions? Okay, so let's learn to our last example. If y'all would take a moment to complete this, read it, think about what strategy you would need. So we know we're going from base 10 to another base. So we put the base 10 number inside the box. What we're trying to turn it into outside, and we start dividing. 231 divided by 5 goes in 46 times perfectly. We need to figure out the remainder though, because it doesn't divide exactly. So 46 times 5, that gets you to 230. We wanted to be at 231, so we've got a remainder of 1. And we continue the process. 9 times perfectly. 5 times 9. We get you to 45. We wanted to be at 46, so we've got another remainder of 1. 5 goes into 9. 1 time perfectly with the remainder. So you've got the 1. 5 times 1 is 5, but we wanted to be at 9, so y'all agree remainder would be 4. Good. 5 goes into 1 0 times perfectly. 0 times 5 is 0. We wanted to be at 1, so our remainder is 1. So if you haven't already, think about how you would write your final answer. Remember, you go upwards and kind of turn it 90 degrees. And y'all agree with 1, 4, 1, 1. And then I do need to write subscript base 5 because this is not the number 1411 because it's not base 10, it's 1411 in base 5. And what is that equal to? It's equal to 231 in base 10.